Hi everybody. How's it going? It's going. Yeah, I don't know. What do you want?
Extra credit.
Sure.
That's all I want.
Yeah. If you find them, you get it.
I'm gonna like start like interrogating people.
Yeah, do it. I know it was you.
Being stingy with the any other classes take a tab.
Here's the problem. Here's the problem. My bet is it was somebody from like econ that walked across the hard part of the calculator that isn't even somebody that I have in class on the reg. You know, like, and that's why they forgot to return it. Just sitting in their backpack or something. Today, though, we're starting chapter 14. Before I get into that, though, I'd like to admonish everyone that has not submitted an IA survey and or even come up with their IA topic, even worse, if you're still working on that. Now, if you are collecting raw data from a different source, that's fine, but like, send me your raw data. Put that on your to-do list for the week, everybody, if you haven't already done so. Now, I have a handful of you guys that have sent me stuff, which is great. But if you are amongst those that have not done this, get on it.
Is there like completed I-2 for?
Yeah. Yeah, that's your final exam grade.
Yeah, it's with our HP. It's not that much.
Yeah. All right. Now let's start chapter 14, eh? Here we go. In chapter 14, we're talking about bivariate data, or bivariate statistics, and we say the prefix bi. What does that mean? Two. Bivariate means two variables. Great. Now, an important statistic when examining two variables are, is there a correlation between the two variables? So all of you that have been using correlation all this time have been using it incorrectly. Correlation has a very specific statistical meaning. It is not causation, but it's not association either, or relationship, or cause and effect. Correlation is very specific, and we're going to talk about that today. So again, bivariate. Data consists of measurement of two variables taken from every individual in a sample. Guess what your IA is? Bivariate, right? Every single person or every single measurement you're taking is going to get two things you're going to get from it. Whether it's like a draft place and a career length, or it's a hours of sleep and the GPA, or whatever. Correlation is the relationship between the two variables, but more specifically than that, we would classify all variables as having some level of correlation between one another. What we're really talking about when we talk about correlation is the strength and nature of that relationship, and that's what we're going to be diving into deeper here. So before you can talk about correlation, you need to choose a independent-dependent variable. So the independent variable is like the cause, and the dependent variable is like the effect. if you're doing an IA about how sleep affects school performance, and you choose to look at the hours that a person sleeps and their GPA, which one is the independent variable and which is the dependent? Oh my gosh. If you're looking at height and weight of an individual, which one is the independent, which is the dependent? Height and weight of an individual. Height is independent, weight would be dependent. Why would you say that?
Because you can't control height.
Typically, the taller someone's going to be, the heavier they're going to have to be, because they need bones and muscles and tendons and stuff to support that height, right? Everybody agree that if you take one person and you just, like, multiply their proportions by like 6/5, they're just going to have a bigger version of themselves, but they'll be much, much heavier, right? Size of someone's hand related to their height. What's the independent? What's the dependent? Height is independent. Hand size is dependent, right? Because you'd assume that as you're growing up, all of your body is growing, including like your hands or your feet or your, head size or whatever. If a company spends more on advertising, will the company sell more of its product? What's the independent variable? Advertising spend, and the dependent would be then
Selling product.
yeah, sales, right? Everybody agree? Feels like that the advertising should impact sales, cause you to sell more stuff. If it doesn't, you need to hire a different advertising firm. One way to study the nature and strength of a relationship is through something called a scatter plot. So essentially all you're doing for a scatter plot is resolving your data into points, x comma y's. So independent variable comma dependent variable, and then plotting them on the graph. So to do that, you determine which variable goes on which axis. Where should the independent variable go? X-axis, right? Everybody's good with that idea? The dependent variable then goes on the y-axis. If you're graphing a scatter plot, those axes need to be labeled in units related to your study, right? So if you're doing Anthony's IA with hours of sleep and GPA, your x-axis should be labeled hours of sleep, and your y-axis should be labeled GPA. Everybody's good with that idea? So after you've labeled and scaled, what do I mean by scale?
Like correct numbers to graph on.
Yeah, you can have some units associated. If you're putting a scale for sleep, what would you potentially want to go by?
Hours.
But how many?
Like 30 half hours.
Okay, 0.5s or 1s. Either of those I think would be appropriate for sleeps, right? What about GPA?
Like 0.1 maybe.
0.1s I think would be appropriate, sure. Now if you get to 40 or 4.0, that's 40 points. So maybe quarters might be easier then. That gives you only then 10 tick marks to 4.0, but depending on how grainy your data is, you might want to go by tens. Okay. Now we're going to talk about how to describe what you see in a scatter plot. This is 100% a quiz question, being able to describe what you see in a scatter plot using the correct vocabulary. So like I can lock in and look at this. So what we're looking for on a scatter plot when we're doing the description is a direction, form, and strength of the relationship. So those are the three things if we're asked to describe a scatter plot, what we should be looking for. Direction, form, and strength. And we'll use specific vocabulary to describe each of those three things in a moment. And the fourth thing is outliers. What does this essentially sound like to you guys? This sounds like socks to me, right? Strength, outlier, center, spread is kind of the same thing. Okay. So let's talk about direction. You can answer your direction in one of two ways. Yes. You can say that the scatter plot or the data set has a positive association, or that it has a negative association. Those are your only two answers. Or you could possibly say roughly no association. What does a scatter plot with a positive association look like? Looks like the data is trending upward from left to right, like it has a positive slope. What would negative association look like?
A negative slope.
It's trending downward from left to right, like it has a negative slope. And what would no association look like?
Flat.
Flat, or it just looks like a splat, like a random scattering of stuff with no discernible patterns. Everybody's okay with that? So that's, what is that the answer to? Direction. Direction is the description that is either positive or negative. Okay? So if we look at this guy, we would say this is negative direction. Okay? So the direction is the negative. The other three descriptors that we want to talk about are the strength. So the strength is how tightly the data is packed together. So you would say things like very strong, moderately strong, weak, very weak. Those would be just examples of ways to describe the strength of your relationship. The stronger your relationship, the tighter that data should be packed together. The more it should look like a single curve rather than like a band of data, but like a straight, well not, but like a single file line, as opposed to like a cluster. Is everybody okay with the idea for strength? The last descriptor is form. When describing a form, you want to think about your basic function shapes. So your forms might be linear, might be exponential, might be quadratic, might be logarithmic, like your basic function shapes that you would have studied in your Algebra 2 and pre-calculus courses. Everybody's okay with that? Direction, positive or negative. Strength, very strong, moderately strong, weak, moderately weak. Form, linear, exponential, quadratic, etc. Everybody's okay with how to answer these parts? Let's look at this guy here. Who can tell me the direction? Positive, good. Who can tell me the strength? Moderate to fairly, yeah, I think that's somewhere in there. I wouldn't say very because it doesn't look like a single file line. And the form. Linear is what I would answer to this as well. It looks mostly like a straight line, right? Fairly thick straight line, right? Like, but a straight line nonetheless. Direction, we say positive association. The form appears to be linear. And we'd say fairly strong, And are there any outliers here? If you look, doesn't really look like it, right? We'll talk about outliers here in a bit, but they're going to be pretty stark for the most part. The next thing we want to talk about is a line of best fit. So when we draw this line of best fit, this is a straight line that best approximates our data. So this is going to be a straight line that we could write a function for that is the best possible linear approximation for our data. So a few key attributes for this straight line, one of which is that it must pass through the mean point. The mean point is the xy, where the x-coordinate is the average of the x values in your data set, and the y-coordinate is the average of the y values in your data set. Hence, mean point, average x, comma, average y. Everybody okay? So, when we draw our mean line, or line of best fit, must go through the mean point. But for now, the slope of our line is going to be just eyeballed. Your goal is to draw this line of best fit so that it's as close as possible to all the data points. Yes, Emerson?
Yeah.
We'll get there. Yes is the answer. And we'll get to how to do that in a moment. Okay. Vocabulary time and how to be careful when we talk about things. Correlation versus causation. I've been teaching in this room, I think this is year 18. This stapler has been sitting in this room the entire time. Never once have I seen a tiger in this room. This stapler repels tigers. True or false?
You never know, false.
What am I confusing?
Correlation and causation.
Correct. Now, is the presence of tigers and the presence of this stapler correlated? Yes. Right? When this stapler is here, tigers have not been. Is the cause of the tigers staying away the result of this stapler? Probably not. What is the likely cause? We live in North America and there's no tigers wandering around here short of a zoo or somebody's exotic pet on loose that they probably shouldn't have anyway. Is everybody okay with the difference between correlation and causation? So stapler, not causing tiger repelling, has no tiger repelling properties that we can determine. What it does is it correlates very nicely with the presence of tigers. But really that probably has a lot more to do with its North American location than anything else. You drop yourself into the Indian subcontinent with this stapler and hope that it protects you from a tiger attack. I think you're going to be sorely, sorely disappointed. Alright. In general, causal relationship, extremely difficult to demonstrate. Correlative one, relatively easy. Does correlation equal causation? Well, that's what you'd hope in the design of your experiment, that you've done a good enough job to where you can make an argument that the correlation you're seeing could be causation. That you have good reason to suppose that. But are you ever really truly sure? Probably not. But like, beyond a reasonable doubt, sure. That's kind of how science works. Everybody okay with the idea? So when you're writing, like when you're doing your IA, or you're writing a response on a test, Should you be using the word cause at any point? Probably not. Should you be using the word correlation? Yes, but only when you're talking about the relationship, the measurable relationship between two variables when looking at a scatter plot. Not the result of a chi-squared test for independence. That is not giving you correlation. Everybody's okay?
Yeah.
Alright, and then I did a tighter example on that, so that's good. Go away. I want the other way. Okay. Now, at this point, we've where's my mouse? Okay. At this point, when we've described the level of correlation between two variables, we've just used words, right? And our eyeballs to kind of eyeball it. Well, that's something, and it is not very good. What we'd like to do is to do this in a more quantifiable way. Let's put a number and a scale to the level of correlation. That's what our goal is to do now. So we're going to do a calculation. That calculation is called the Pearson Product Moment Correlation Coefficient. That's what PMCC stands for. I know that's a lot of words. No. But if you're writing an IA and you want to identify what it is you're naming or you're doing, you probably want to use its name, but that's always something you can look up, right? Like you don't have to ask you to write that down on a test. The symbol we use to represent that calculation is the lowercase letter r. Yes, it's the pirate's favorite statistic. What that statistic does is it measures the direction and strength of a linear relationship between two quantitative variables. Note it is describing the linear strength of the linear relationship only. So some facts about R. R is always between -1 and +1. Values, if you give me an R value less than -1, I'll give you no points for that problem. If you give me an R value greater than +1, I'll give you no points for those problems. Those are impossible answers. Must be between -1 and +1. R values that are positive mean that the graph has a positive association. R values that are negative indicate that the graph has a negative association. Values at or near 0 indicate a very weak linear relationship. Now, strictly speaking, if you're putting a finite data set and calculating an R value for it, you're not going to actually be able to get a 0 value for R. It is impossible for that to happen. It's like a theoretical value only. But if you're like 0.00 whatever, it's like that might as well be 0 there. The strength of the linear relationship increases as R moves away from 0. So the closer you're getting to 1 or -1 means your data is getting more and more linear. And the extreme values, -1 and +1, are possible. What that means is there is a perfect linear relationship for your data set, meaning that every point in your data set would be a point on the exact same line. So if all you have is 2 points in your data set, you're always going to have an R value of 1 or -1. Because what do we know from geometry? 2 points define a straight line, right? So your data set is just 2 points. You're always going to have a straight line through them. You always have an R value of 1 or -1. Just the breaks. Everybody's good? Alright, so when describing the strength of our linear relationship, we're going to give some ranges for R and attach words to them. So we're going to quantify that process that we were doing before. So R values between 0 and 0.25 are very weak. Values between 0.25 and 0.5 are regular weak. Between 0.5 and 0.75, moderately strong. 0.75 to 1, very strong. Now note these are absolute value relationships, so the same thing applies to 0 to -0.25. I should say -0.25 to 0, or the same thing from -0.5 to -2.25, etc., etc.
So if it was like 0.5, would it be weak from one relation?
Well, where is the inequality at?
Oh.
It would be weak, right?
Yeah.
Good enough? Everybody happy? Okay. Would you have to remember this? Yes. Yes. This is one that I would expect that you remember, although, goodness gracious, the divisions are pretty stinking easy, right? There's just 4 divisions and they're all by a quarter. Not bad. All right. So visually, what do these values for R look like? So the first scatter plot has correlation approximately 0. Just looks like a random scattering, right? Look at the second scatter plot. Not a whole lot less random, but if you look carefully, you can kind of see there's a slight downward trend in the data, but it's still pretty random. So we got negative direction, but very weak or weak correlation. The third scatter plot has correlation 0.5. Again, you can see a little bit easier to see an upward trend in our data. It still doesn't look very much like a line, but it's a little bit more clearly trending upward than the previous. Everybody's okay there? If I look at the first one on the bottom, again, clear downward trend, and this time the data's clumped closer together. If I were to think about it, oops, where did that go? Stay. If it's a line, like the thickness of this line is a little less thick than the thickness of this line, right? You can kind of see that. So it should be a little bit better fit. Here's an example of 0.9. Looks much tighter together. Still not super duper thin, but better than before. And then our last example, -0.99. Boy, that's pretty darn tight, right? Am I good? Just to give you a visual example of what you're looking at. All right, let's do some examples. Somebody want to give me an estimate for R? Anthony.
0.8.
What?
0.75.
0.7 plus 2. 0.7.
0.75.
I think you're undershooting it.
Yeah.
0.8.
I said point. Ow! 0.85.
No.
0.8 or 0.7.
Giovanni said 0.3. That's embarrassing.
I didn't.
I think this is
0.6.
in the 0.9s.
Really?
Yeah.
But the points at the top are too far down.
I don't think it matters.
You don't think so?
Yeah.
You
You said
figured it 7, right?
Sometimes outliers.
Okay, what's the direction?
Positive.
Positive. What's the form?
Linear.
Linear. And the strength? I would say this is very strong. Yeah, this is between 0.75 and 1 for sure. Well, I need to go look look at my answers over here on the side. What does this say? It was 0.8 was what I had written down for this. I am surprised by that, but okay. All right, let's take a look at this guy. Estimate for R.
0.3.
I think that's pretty reasonable. It's bad, right? The direction is positive, agreed. The form is quadratic.
Upside down. Or
Oh, you think it's an upside down quadratic?
like U, upside down.
Yeah, I think this guy at the top is ruining that for you.
Yeah. That'd just be like.
I'd still call this linear.
I'd say linear.
It's just not. I think that's the best you're gonna do. And the strength here would be weak or very weak, right? Yeah. Okay. How about this guy?
That's no correlation.
I think you're probably right that this is darn R would be close to 0. Very weak. You know, no real form here to this. I guess call it linear if you want. Like horizontal would be the best probably you're gonna get, but you have this little guy down here that I don't know what it's doing.
.1 or negative. It's like
So I would
negative.
say no.
Yeah.
Absolutely.
No, there's pretty like it's very terrible.
I'd say -1.
Yeah, I think the
Negative
Grande
one,
is
that's
right.
strong. That's strong. -1. Are you serious? Are you serious?
-1 is super wrong.
That's so terrible.
No, you said that's not what I said.
I said -0.1.
Yeah, I think that weak negative is appropriate there. So if you think it's like -0.2 or 0.3 or something, I think that's 0.1, like in that neck of the woods. I'm not going to ask you to be like super precise on these. I think like within a couple of tenths is probably the range. Like I'll have a number, then it'd be like plus or minus a tenth kind of thing. Would be the level of precision I'd be looking for from that. And even that might be asking a lot. Alright. So let's talk about, we've talked about this R value. Let's talk about how we calculate this. So some facts about the calculation of R. There will be no difference in the value for R, regardless of which variable you call the independent or dependent variable. That R is resilient to that that determination. R will not change if you do a unit conversion. So if you have like Anthony's collected some hours of sleep and some GPAs, if he says, oh, you know what, like I'm gonna do this in minutes of sleep instead and converts all of his hours to minutes, value for R will not change, even though all the data points changed. Is okay? That R statistic has no unit of measurement attached to it. It's not hours, it's not GPAs, it's nothing. It's just a number. Now, some things to be careful about. To calculate a correlation, both variables need to be quantitative. Like for your IA, where we ask that both variables are quantitative. A correlation will not do a good job at describing a curved relationship, like a quadratic or exponential, regardless of how good that relationship looks. Like if something looks like a perfect parabola and you calculate an R value for it, it's still going to stink. There's another statistic you can use for it. And we would would say that the correlation is not resistant, meaning that the presence of outliers can strongly affect your value for R. I think I have a slide here coming up where we show 4 different graphs that all have the same R value that are just shockingly different. Just shockingly different. And then keep in mind that it's not a complete summary of the data, right? There's a lot more that you could learn, a lot more going on than just the correlation. All right. Here's the calculation for R. 1 over n. N is the number of measurements in your data set, and it's the first data point minus the average, or the first x data point minus the average of x's, divided by the standard deviation of the x's, times the first y data point minus the average y, divided by the standard deviation for y, and then plus the same thing for the second x and y, plus the third x and y, and so on and so forth, all the way until you've counted all of your x and y's in this fashion. Okay? We should be able to do this both by hand and with our calculator. Everybody's okay with that? So we'll talk about how to do it by hand with your calculator, and then just calculator, give me the number. All right. So notice here we have a scatter plot. The two variables are miles driven and price in dollars. So this is in reference to like the value of a car. Hopefully, as you know, the value of a car decreases as you put more miles on it. If we flip the axes, notice that the line of best fit has changed, but the R value remained the same, right? Here it's written as R squared because that's the summary value that the that Excel gives you. Everybody's okay? Okay. Take a look at these 3 or these 4 scatter plots here. Guess what? They all have the same R value. Can you believe that? That is crazy, right? I have to go look. I forget what the R value is, but I'm sure I have it on the notes.
Wait, what kind of graph is B again? What is that?
B is a quadratic.
Oh, it's a ball.
Which one's exponential?
None of these are exponential. I know. Looks like the graph of like y equals e to the x, where it has a horizontal asymptote as x gets very small, and then shoots off very quickly as x gets big.
Oh, we have to know that one.
Probably. Right? Look at this. Bonkers that these all have the same R value. They're all about 0.8. What's ruining the R values in some of these cases? Yeah, we have some crazy outliers, right? If you kick this outlier out, what would you expect the R value to be? 0.99, right? Real darn close to 1. How about for this one? Same thing, right? Real close to 1. Here, there's no outlier to speak of. Here, there isn't one either. It's just not a straight line or linear relationship, right? It's kind of linear until you get to like the leveling off part. So the exact same R values, they'd have the same lines of best fit, but clearly very different data sets. What I want to look at next is, hi, come on in. Kevin, you're leaving early today.
Kevin, bro.
But not if he doesn't wake up. Yeah, man.
Thank you.
Yeah. So here's what I want you guys to look at. We have two outliers here, child 9 and child 18, right? Or 18 and 19. Well, it's an outlier in the x direction. While child 19 is an outlier in the y direction. You guys see that? Which one of those do you think is going to have more effect on R if they are removed?
Oh, if they're
No, 19. If they're removed. Oh, 19.
I thought he meant like.
18 makes it strong.
Yeah.
Let's see. With all 19 children, the R value is 0.64. Removing child 19 improves your R value to negative 0.76. If we remove child 18, it worsens your R value to negative 0.33. So just because something is an outlier in one direction or the other doesn't necessarily mean it's going to improve, by removing it, it's going to improve your R, right? So if you look at child 18, that's quite close to the line of best fit. That's actually helping you out a lot, as opposed to child 19, which is very far from the line of best fit, which is not helping you out. Of course. Is everybody okay with that? So just because something's an outlier doesn't necessarily mean it's going to, removing it's going to help your R value.
Makes sense.
Okay? Alright. So a little bit about one way to compute these lines of best fit. So one way to do that, go back, is basically you draw a line from your point back to your line of best fit, and then you kind of turn that into a square by just like tracing over the same amount and then tracing back up, and you basically make a square. And you do that for every single data point and compute the area of all those squares. And what you want to do is you move your line of best fit around so that all those areas are minimized. Doing it that way is the technique's called the least squares line. When your calculator does the lin-right command, that's kind of what it's doing. But it doesn't really do it that way. That's the result, though, is you get that kind of a line. So we say least squares line, that's what I mean. Make the sum of the squares of the vertical distances to the points as small as possible. A point that is extreme in the x direction with no other points near it will pull the line towards itself. We call such points influential. So if I go back and look at this, so this guy is an X outlier, right? So we call that point influential. An observation is influential for a statistical calculation if removing it would markedly change the result of the calculation. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. That's what we just saw there, right? Was when we removed that child 19, it just tanked our R value, right? we went from moderate to Hoopsville. Everybody okay? So, to this point, we've talked about the R statistic, which measures the strength of a linear relationship, right? But we saw, like, some of these guys were like, this doesn't really seem like a linear relationship at all, right? Like, can I measure something like that? Is there another statistic that I could use? So I'm going to introduce that with what's called the Spearman's rank correlation coefficient. So you have Spearman and Pearson are the two correlation coefficients. The Spearman coefficient ignores the type of relationship between the variables, so it's going to ignore form. It only measures if there's a consistent relationship between the variables, i.e., is it increasing or decreasing? So, some facts about the Spearman coefficient. The notation we use for the Spearman coefficient is R sub S, or we could use this Greek letter rho, which looks kind of like the letter P, but it's not the letter P. It's not written as a letter P. It's the Greek letter rho. The Spearman coefficient is always a number between -1 and 1, just like R. Spearman values greater than 0 indicate positive direction, and less than 0 indicate negative direction, just like R. Values near 0 indicate a weak relationship, just like R. The strength of the rank order relationship increases as RS moves away from 0 towards -1 or 1, just like R. The extreme values, -1 and +1, occur only in the case of a perfect rank order relationship, just like R. Guess what, guys? The calculation for Spearman is the same after some modification to our values for x and y. So we're going to change our x's and y's, and we're going to do the exact same calculation for r afterward. Everybody okay? Yes? Sure. All right, so let's take an example here. Mobile phones lose their resale value quickly after they're purchased. The following data is collected for one particular model. What you have is the percent change in value and the month that it, or how old the phone is in months. Everybody, you see that? Looks okay. So here's like a scatter plot for this data. Emerson, what form does this scatter plot look?
Exponential.
Yeah, this is what an exponential looks like, right? Where it's, where's my guy? Where's my pointer at? I lost him. Oh, there he is. Where it's whoop, but then flattens out, right? This is like a exponential with like a negative, like 1 over e to the x, has a negative exponent to it, but like, whatever, still exponential. The Pearson correlation for this is -0.87. It's a very strong negative relationship. Now let's calculate the Spearman. So the first thing I'm going to do is convert my XYs into rank order data. So to do that, I just relabel my X's and Y's in rank from highest to lowest. So for example, 24 is the highest amount, so that gets rank 1. 22 would get rank 2, and so on and so forth, all the way down to 0 getting rank 13, because I had 13 total data points. Sure. And then we do the same thing for the second column. Observe, though, that these two columns are going to be ranked differently. So this is what I get. That's my new rank order data. Everybody's okay? To get the Spearman coefficient, all I do is I take that rank order data and do the same R calculation for it. When I do that, I get negative 0.995. Ooh, doggy, that's a strong relationship there, right? Is it talking anything about its linearness? No. It's talking about its decreasingness, which is very strongly decreasing. Which you'd expect, right? For all of a sudden your phone doesn't get more valuable, even though it's a year old. Where could that happen, though? Give me an example of something where initially you own it and it loses value, but if you own it long enough, it becomes more valuable.
Pokemon cards?
Okay, maybe. I don't know much about Pokemon cards. That's not the example I was thinking of. Property, maybe, probably not. Property tends to go up. Brooks?
Old coins are like vintage things.
So like things that have like collectability. I was thinking specifically cars, right? Like you own a car, loses value every year over year until it gets old enough that it's now a classic, and maybe it starts becoming valuable because now it's rare because you're the only one that kept a decent like 1960s Chevrolet in order or whatever. Right? You guys kind of get the idea there?
Yeah.
Now, are there a lot of things that do that? Probably not a ton. You know, like most things that are designed to be collectible gain value, like, or never lose value, right? Like if you're talking about like comic books or baseball cards or something, you know, like if it was $1 comic book, it's probably still $1 comic book 5 years later, even if nobody wants it. Now, if you wait 100 years, maybe all of a sudden it's a $100 comic book, but probably not if it's a now printed, because they print so many of those things now. And people know to collect them, but they're still not going to be that rare. You know, like, for example, the Model T, not a very valuable collectible car, because they made a bajillion of them. You know, there's just like millions and millions of them made, even though it's really old. It's not rare. And they were basically tanks. They lasted forever. You know, like. Alright, blah, 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 blah. Okay, so what if we reverse the rankings? What if accidentally we did this instead of going from like highest to lowest, we went from lowest to highest? Oh no! We made a mistake! What's gonna happen? I do the same calculation. Oh, look at that. Did I get the same graph? With the same relationship? With the same RS value? Oh, thank goodness. I don't have to worry about like screwing that up on the test. I just have to pick one and do it. All right. What happens if there's ties, though? What do I do if there's like a tie? So notice that Kevin and Steve both studied for 3.5 hours. And Anton, Julie, and Lucas all studied for 6.5. I have 2 ties. How do I order them from greatest to least with a tie? Oh no! Well, this is what you do. So, this is the correct ranking, what I've done here. So Cindy still is 1, biggest value. Lucas, Julie, and Anton all tied for second. They don't get second because they tied for second. They get the average of second, third, and fourth place. I add up second, 2, plus third, 3, plus 4, 4. That gives me 11, and I divide that by 3. That's going to be their new ranking. Give me a second. Okay, we've ranked now 4 things, right? So the next ranking after that should be 5th, because there was a tie at second place for places 2, 3, and 4. And then we'll go 6, 7, 8, 9, and then another tie at 10 and 11. So the ranking they're going to get is not 10. It's going to be the average of 10th and 11th place. So this is what we're going to show you. So if there's a tie, that's how you handle it. They get the average of the places that are occupied by the tie. What does this remind you of? Yeah, I was thinking like a real world thing. Were anyone on the track team?
Yeah.
This is how a track meet is scored if there's like a tie in the high jump or something. The points for second place, if you have a tie at second and third place, is going to be the average of the points between first or second and third place, and the next person gets 4th. So there'd be like no third placer in the meet.
Wait, why do you add 2 plus 3 plus 4 then?
Because there was Anton, Lucas, and Julie occupied places 2, 3, and 4 in the ranking. So the ranking we give them is the average of second, third, and fourth place. This is going to be the hardest thing in this chapter, is handling ties in the
Because
spearmint.
they all tied, but they had to get first, second, third place.
Those rankings have to be accounted for because they were all tied there. They occupy second, third, and fourth places. Which one gets which? Well, none of them get first, second, or third. They get the average of those places. And then the next person after them gets 5th. This is the hardest thing in the chapter from a calculation standpoint, is getting that straight. And then once we have our proper rank order data, we just do the Pearson calculation on our rank order stuff, and it spits out the spearmint statistic. Notice that if I didn't do the rankings properly, if I forgot to average the places, notice I do get the wrong spearmint statistic, right? If I just said, oh, Anton, Lucas, Julie all tied for second, Jim's 5th, 6, 7, 8, Steve and Kevin both tied for 10, give them both 10, you get the wrong value. All right, let's do some comparisons between Pearson and spearmint statistics with regard to an outlier. Here's my graph. I got one crazy outlier, right? It's an outlier in both the X and Y directions. The Pearson statistic, 0.75. The Spearman statistic, negative 0.48. Notice that one PMCC, or that one outlier for the Pearson, if I look at the overall trend of the data, it should be negative, right? All the data lines up in a pretty strong negative line, except for that one stupid outlier. Look at what the outlier did to our Pearson statistic. Made it positive. That data should not be positive. It's a huge effect. Spearman, though, still comes out negative, right? The outlier does not affect it in nearly as strongly because the rank order data, only allows the outlier to affect it only so much. Like the outlierness is almost going to be the same regardless of how big of an outlier it is. The Pearson, the size of your outlier definitely makes a big difference. Spearman, not so much. Next thing to talk about is monotonicity. So we say a function is monotone if that function is either increasing or staying the same. We say that's monotone increasing, or decreasing and staying the same would be monotone decreasing. Everybody's okay with that? Or monotone up and monotone down? So if I look at some examples of three sets of functions, the top three functions are all increasing. They're all monotone increasing, right? They're increasing or staying the same at every value. The bottom ones are monotone decreasing, again, decreasing or staying the same for every value x. These ones are not monotone. Notice the first one starts increasing and then changes to decreasing. Same thing with the second one and the third one, right? There's a change from increasing to decreasing somewhere along the way. Here's the thing. If you look at these three different increasing graphs, they're all going to have the same Spearman statistic, and the three decreasing graphs are all going to have the same Spearman statistic. Will they have the same Pearson statistic? No! Right? Clearly the last ones are crazy linear. Those should have R values around 1 or -1 respectively. Everybody agree? The other one's not nearly as linear. Okay. Anyway, that's the gist of it. This will stop us for today. You can take the last 15 minutes or so to yourselves. You guys should be able to do now, though, sections 14.1 and 14.2 for homeworks. Which is page 469, 1 through 10, and then 479, 1 through 12. Okay.
Like, okay, man.
Next time, if you remind me, please do. We'll do the in-class examples for these and show you how to do some stuff on the calculator. Deal? Okay. All right, this is me signing off.